Hi, welcome to this video. Today we're going to be looking at threading on the lathe. Now, threading on the lathe is a form cutting operation, and that means that our cutting tool imparts its shape to the part. That means that if our thread is going to be an accurate 60-degree thread, our tool has to be very accurately 60 degrees. Now, when we're sharpening our tool, we can rough it out using one of these fishtail thread gauges to measure our 60-degree angle. But if we're going to be turning an accurate thread that we're going to want to measure with the 3-wire method, well, we're going to want to measure it a little better than visually with this gauge. And for that, we're going to be using our optical comparator, because I'm going to want this tool to measure 60 degrees well within 20 minutes of a degree. And that's something that's difficult to see without magnification. So let's take a look at how to use this optical comparator. Oh, by the way, should you not have an optical comparator, but you still want to produce threading on the lathe, you have two options. Produce less accurate threads using cutting tools that are sharpened a little less accurately, and that's okay for most threading applications, or buy pre-formed threading tools. There's a lot of carbide tools out there that are already formed for specific thread angles. In this case, 60 degree is the most common thread angle. So perhaps for this operation, instead of sharpening your own, especially if you're just starting out, maybe it'd be best to go out and buy yourself one. Regardless, we're going to look at our optical comparator. For starters, we're going to deposit the tool on the optical comparator's glass table. We don't have to align it well at this point because we're going to use our XY axis as well as our rotary scale to align one of the two cutting edges with a line on the rotary scale. So we're going to make sure that it's really well aligned. Be very careful. It's the starting point of our measurement. And then, once it's well aligned, we can set our rotary or angular scale to 0. And now, using the rotary or angular scale, I can now move the line that I lined up earlier, my reference line, over to the second cutting lip of the tool. And that'll give me an accurate angular measurement for the point of this tool. So we can see that we have 59 degrees 53 minutes, well within the plus or minus 10 minutes tolerance that we'd given ourselves for the angular point of this threading tool. We're going to now, before we move on, take advantage of the fact that the part is on the optical comparator to take a look at the tool nose radius. So let's start by repositioning the tool at a place where we can see the point a little better. What we're looking for here is the tool point radius, or the radius at the end of the tool. What you have to understand is the tool consists of two cutting lips. So we have one cutting lip here and one cutting lip here. And the two cutting lips, well, they're joined by the tool nose radius. Now, we don't want this tool to be perfectly pointy because the point of a tool has no surface and cannot lift the chip. Luckily, the unified thread form accepts a small radius on the point of the cutting tool because the root of the thread is slightly round. But remember, it's important that it's just a slight radius, and the edge of the radius has to be very sharp. We're going to produce the radius on the end of this tool with a honing stone after it's been ground on the pedestal grinder. To perform our threading operation, we're going to need certain tools. To start with, our 60-degree threading tool and a thread gauge or a threading gauge, often called a fishtail. We're going to use that to align our tool. Now, since we're going to be cutting a 5/8 18th thread, we're going to need a 0 to 1 inch micrometer, and that's what we have here. Since we're going to be measuring our thread using the 3-wire method, well, we're going to need a set of wires for thread measurement. A thread pitch gauge is always a good thing to have, and as the name says, we're going to use it to check or to verify the pitch of our thread. Now, we're also going to need a calculator because there is quite a few calculations to perform to find the proper dimensions, the ones that we're shooting for, and obviously our piece of blank steel.
Well, unlike Sheldon Cooper, most people just don't enjoy doing the math. But in a trade where precision is everything, getting good numbers is very important. And sometimes we have to do the math. And to do the math, we have to start out with good numbers. And where do we get those numbers? I prefer to use the Machinery's Handbook. And I have an older edition here. I think we're up to the 29th or 30th edition. This is the 23rd. But for threads, this is just fine. Any old edition will do. I get from the Machinery's Handbook in the famous or infamous Table 4 on unified screw threads, the numbers that I need to cut my thread accurately. So let's take a look at those numbers on the board here. I've decided to cut a 5/8 18 UNF Class 2A. Now what does that mean? 5/8 is my nominal major diameter. Nominal because 5/8 is the outside diameter of the thread, but not exactly. Our thread is going to be a little smaller than 5/8, but 5/8 is the closest whole fraction. Now, 18 is, and this minus isn't a minus, it's just a divider. So 5/8, 18. 18 here is my number of threads per inch. Be careful, that's not the pitch, it's the number of threads per inch. The pitch of this thread is going to be 1/18th, okay, and that's important. UNF, Unified National Fine Series, Class 2 means that it's a medium precision thread. A little too accurate actually to be done with a die by hand, so we're going to be cutting this one on the lathe. And Class 2A, A here meaning external thread. So 5/8 18 UNF 2A. And the numbers we need to produce that thread, well, we need to know the major diameter, the minor diameter, the pitch diameter, the wire diameter, the pitch as such, and then we have to calculate our major over the wire diameter and our minor over the wire diameter. So let's take a look at that a little more in detail and why each one of these numbers is important. Well, first things first, we have to turn a blank if we want to thread apart. And what diameter am I going to turn the blank to? Well, that's why we need to know the major diameter. And we have it right here, 0.6236, 0.6149. Why two numbers? Two numbers because we have a tolerance to respect. We have to keep our major diameter between these two limit dimensions. So 0.6236, 0.6149. Now, that means that if we're in between that, we're okay. But why is it important? Well, the major diameter has to be a little smaller than the nominal major diameter, because if it isn't, our thread is going to bind. The crest of the outside thread is going to bind in the internal thread. It's really only important to get this diameter accurately to make sure that the crest doesn't bind. Once we have that diameter, we can forget about this measurement. It has nothing to do with the later calculations. Second measurement that we need to have, or numbers that we need to have, is the minor diameter. And you'll see here that I haven't put a tolerance. I've just put the major minor diameter, or the biggest that the minor diameter can be. And that's 0.5575, so 557 thousandths of an inch. We can forget about the 5/10,000ths there. Why do I need that minor diameter? I'm not going to be measuring it. What I'm going to do here is I have to produce a thread clearance groove at the end of my thread. And what diameter am I going to produce it? Well, I'm going to produce it at this diameter. So this is the largest we can have. So 5/57,000ths or a couple of thousandths smaller. No big deal. It's a thread clearance groove. So somewhere around 555 will be just fine. 555,000ths of an inch, that is. The next number that's important is a number that we don't really use very often and that very few people are aware of. And that is the pitch diameter. And the pitch diameter is the diameter of an imaginary cylinder that passes through the middle height of the threads on a part. It's actually the diameter on which our threads contact, because threads don't touch on their root and their crest. Threads touch on their flanks, and that's why it's so important to have the pitch diameter. We're going to measure the pitch diameter using the 3-wire method, and we're going to see that in the rest of the video, so don't worry about that. But it's important to have these numbers, not because we can see them, they're imaginary, it's just an imaginary cylinder, but because we're going to use these mid-height numbers to calculate our measurement over the wire, our maximum measurement over the wire, and our minimum measurement over the wire. So our pitch diameter here, we have 0.587 thousandths of an inch and 0.582 thousandths of an inch. And in our formula down here, the pitch diameter, we're going to use E as the letter that represents that variable. Why do I have two numbers here? Again, we have a tolerance to respect. So the largest the pitch diameter can be, and the smallest that the pitch diameter can be. And that means that this formula here that we're going to do later on, in a few minutes actually, well, we're going to do it twice. We're going to calculate M, which is my measurement over the wires. We're going to calculate M once with the largest pitch diameter, and that will give me my maximum over the wire measurement. And I'm going to calculate it a second time with the smallest pitch diameter, and that obviously is going to give me my minimum measurement over the wires. So very important. And we'll be looking at the measurement over the wires in a few minutes. The next number that we need, well, obviously I just sold the punchline. We're going to be measuring over the wires, so we need to know the diameter of the wires that we're going to use, and we're going to be using 3 wires of the same diameter. And if I look at my chart, I find that I'm going to need a 32 thousandths of an inch diameter wire, and it's going to be represented by the variable W. The pitch here, well, it's, as I mentioned at the very start, is 1/18. My number of threads per inch here is 18 threads per inch. If I want the pitch, and the pitch is defined as being the distance that a thread advances or progresses actually along the part in one turn. Well, if I have 18 threads in 1 inch, 1 turn of thread is going to be 1/18. So that will give us 0.0555 inches, and that is our pitch. That means that our thread goes once around the part every 55 thousandths of an inch. And that's what we need. So we have our variables in our formula. The formula for the measurement over the wires is M equals E minus 0.86603P plus 3W. This magic number here, 0.6603, well, it's a constant that's derived from the fact that we have a 60-degree thread. So this formula here will work for any thread that has a 60-degree thread form. And that includes most metric threads. Use the same formula. But obviously if you use a metric thread and this formula, all the numbers that go into the formula have to be in metric, okay? But we have all our variables. We have our M that we haven't found yet, but our E is our pitch diameter. We've found those numbers. Our P here is our pitch, and we've found that number. and our W is our wire, and we found that number. So we have all the numbers to figure this out. We're going to do the formula twice, once with the smallest pitch diameter and once with the largest. I won't go through the calculator thing with you. I don't think it'll be very nice on video, but trust me, if you calculate this with these variables, you're going to end up with a maximum measurement over the wires of 0.6353. We're not that accurate. Forget the 10,000ths of an inch. It's really 635 thousandths. That'll be just great. And a minimum of 0.636, so 630 thousandths of an inch as our minimum measurement over the wires. So when I measure my thread over the wires, and if I'm within these two limits, well, my pitch diameter is good and my flank contact on my threads should be just fine. The crests and the roots shouldn't rub because I've respected my major and minor diameters. Everything should work out just fine. So let's get back to the lathe and get going with this threading operation.
Okay, before we start to adjust angles and tools and physical stuff, let's take a quick look at our gearbox as far as feeds go. Now, the gearbox on this machine is separated into two parts. Down at the bottom here we have the normal feed charts, and up at the top here we have our inch threading feeds. So we want 18 threads per inch. So if we look at this chart for 18 threads per inch, we'll see that we need C2SY. So C, S, Y, and 2. That should give us our 18 threads per inch. So CSY2. Since this is our first threading experience and we're going to be threading a right hand, we're going to set it to the lowest speed possible. And we're obviously going to be threading from the tailstock to the headstock, okay, in that direction, because it's a right-handed thread. So my part is already installed. I've mounted it in a 3-jaw chuck, and I've turned it and produced the radius and chamfer without moving it in the 3-jaw chuck. So everything here is concentric and will stay concentric as long as I complete my threading operation without moving the part in the chuck. I have already turned the outside diameter to 620 thousandths of an inch, which is well within our tolerance. I've produced my thread clearance groove at 550 thousandths of an inch, and I've produced a 30-degree chamfer on the end of the part to help with the thread engagement at the very start of the threading operation. So this part is good to go. We can now verify that the thread chasing dial is properly positioned and that its gear is well engaged with the threading lead screw. There, that looks just fine. We can then position our compound rest to a 29-degree angle from the cross feed axis. So 0 degrees, 29 from the cross feed. There you go. Tighten that down well. Now we can install our 60-degree cutting tool and adjust its height. It's very important that the cutting lips be exactly on the center of rotation of your part, or if you prefer, at height 0. With our compound rest adjusted and our height adjusted, we can now move on to adjusting the alignment of our tool. And for that, we're going to use our fishtail or our threading gauge. Now it's time to eliminate the backlash on the compound rest axis and the cross slide axis by bringing the tool up to the part always in the same direction, till it just barely touches it. Once there, and without backing up your hand wheels, position the collars on the scales of your axis or your micrometric collars to 0. We're now ready to start cutting our thread. It's very important not to lose the relation between the rotation of our chuck and the rotation of our lead screw. And for that, we're going to be using our split nut lever. And we're going to engage the split nut lever to start threading, depending on what we see on our thread chasing dial. Since we're cutting a 5/8 18 threads per inch thread, and that 18 is an even number of threads per inch, well, any line on the thread chasing dial will do to indicate when to engage our split nut lever, and thusly ensure that we return back to the same groove each time. We're cutting a single start thread here. We only want one groove. To avoid confusion during threading, we're always going to use our cross slide axis to pull out, come back to the start, and return to 0. It's always going to be on 0 when we cut. Our depth of cut, however, will be taken with our compound rest, and it's always going to move forward. Whereas the cross slide axis is going to retract, come back to the start, and return to 0. And that way we won't get lost, because we don't have to remember where we were the last time we took a cut. So I'm going to back my cross slide up, return to the start of the thread, come back to the 0 that I had set on my cross slide, and take my first depth of cut. A very light cut for this first pass. Now I'm positioned for my first cut, a very light cut. Actually, I'm just going to come and scratch the surface of the part, and I'm going to use the line that I've scratched to verify that my pitch is properly set. Once I've started the lathe up, I'm going to have to wait for my thread chasing dial to line up properly with the line on the casing of the thread chasing dial, and at that moment I'll be able to engage my split nut lever right here. Now, my thread is 18 threads per inch, so any line on the thread chasing dial will do. I can engage on any of the lines. Now, once I've engaged the feed, I'm going to have to be ready to disengage it rapidly, because I have to stop the tool in that thread clearance groove at the end of the thread, and that's not very wide. So with my cross feed, I can back the tool out, come back to the beginning of the thread, and return to my original 0. My tool is exactly where it was at the start. And now, with my compound rest, I can take a second depth of cut, about 0.010 of an inch. But before that, we're going to verify our pitch with our thread pitch gauge. Having selected the 18 threads per inch comb on my thread pitch gauge, I can now come and verify if the pitch on my part is correct. Now I can see here that everything seems good. Yeah, everything's okay, everything lines up, so we can keep going with our threading. Remember, this is a form cutting tool, so the deeper we go, the larger the chip is going to be. So we should reduce our depth of cut progressively with the number of passes that we make. Our first real pass was a 0.010 of an inch on our compound rest. So that's a 1-to-1 ratio. So we're really taking off 0.20 of an inch. Our second cut should probably be around 0.007. The third cut around 0.005, and so on. Remember, our compound rest has a 1-to-1 ratio. That means that it cuts on the radius. So our final passes, however many we need, should be taken at 2 or 0.003 of an inch depth maximum. Okay, so the thread that I'm producing is seriously starting to look like a completed thread. So it would be a good moment to start to measure. We're going to use our 3 wires to measure the thread, and we're going to deposit them in the thread in a fashion that positions them opposite one another. And then with the micrometer, I'm going to snug them down to the part. Just snug. We're using 3 wires here to ensure that the tool, the micrometer in this case, is perpendicular to the part. If each wire is tightened equally, well then the tool will be perpendicular. Okay, that's just snug, so let's take a reading. I can see here that I'm about at 648 thousandths of an inch. Now, what I'm looking for is 630 or 635, somewhere between those two limits. So I still have a little cutting to do. Now I want to keep a good contact on the wires. Make sure that everything is nice and snug. There, that's perfect. So let's take a look. 631 thousandths of an inch. Well within our tolerance. This part is done. So my threading is complete. I have no other operations to perform on this part, so I can pull it from the 3-jaw chuck and move on to what's really important, cleaning up. And remember, threading is a finicky operation. 90% of the battle is preparing and planning. Everything should work out just fine as long as you stay concentrated and follow the steps attentively right up to the last cut. And remember, it's supposed to be fun. So, happy machining!
So all I ever wanted was a little monkey from you.